So far, we have seen a lot about IIoT in this activity. So I'll prefer to talk more about software-defined networking and its role in industrial Internet of Things. So this presentation is divided into three modules. In the first module, we look at the foundational concepts of network automation. Later, I'll give a general overview about network automation and some of its benefits. I'll explain quickly. I'll then quickly explain the logical planes of network functions, the data plane, control plane, and the management plane. So I'll explain what they are because they are essential to understand software-defined networking. Also, while introducing SDNs, I'll also introduce data serialization and also APIs. As I said, this presentation will be an introduction to all these topics. So, however, we planned this session such that we have enough time for discussion at the end. Uh, I will be glad to respond to your questions, or you may simply Google them. You'll find a lot of information. So let us look at network automation first. So how do you connect to a network device? Usually, there are a couple of ways to connect to the network devices. So in the traditional method, engineers manage devices one at a time by connecting to their command line interface via secure shell SSH. But network engineers usually prefer this CLI based interaction with network devices. Telnet connections are also possible too, as well as connections to the console port of the device itself is also allowed. Uh, some devices support a graphical user interface also. So of course, if you are connecting to your device for the first time, you have to use its console port. Many modern network devices have a RJ45 type console port. Although some devices come with a USB mini B console port, most of them support RJ45 type of console ports. So, but the main point is that devices are managed and configured individually. So uh, let us say some for some example, let us assume uh, you want to add a loopback interface to all the routers in your company's network. So first you connect to a router R1 for suppose using a secure shell protocol, configure the loopback interface, save the configuration, and then exit. So similarly, you'll then log into router 2 and router 3. So you have to repeat the same process for each one of hundreds of routers in your company network. So what are some downsides of managing a network like this? First, typos and other small mistakes are common. So these typos can take a lot of time troubleshooting to find that the problem was just a typo in an IP address, for example. It is also time consuming and can be very inefficient, especially in large scale networks. So it is difficult to ensure that all devices adhere to the organization standard configurations. So an organization usually have a standard configuration template that they use for their devices, and it is important to ensure that these policies are upheld throughout the network. So however, as network engineers make changes over the years, the configurations can start to drift away from the standard. So this can cause issues down the line, for example, making troubleshooting difficult because the devices don't all have a similar configuration. So some benefits of network automation are listed. First human error can be reduced, uh, like uh, typos. Instead of a network engineer directly logging into the CLI and manually entering commands, the task can be automated. So network automation allows you to avail such benefits. Networks can become much more scalable because you have a centralized control. Uh, in any size network can be controlled from a remote location, so they become more scalable. New network deployments, network wide changes, as well as troubleshooting can be implemented in a fraction of time. These are all the benefits of having a network wide um, configuration templates. And the improved efficiency of the network operations reduces the OPEX, meaning the operational expenditure of managing the network. Each task requires fewer manpower, and so that engineers can spend more time in managing more important things. Note that there are various tools and methods that can be used to automate the networks. Here are some examples. First one, SDN itself. We'll be looking at SDN in a while. Ansible, Puppet, Chef, etc., and some Python scripts and many more are the possibilities for automating network tasks. So to understand SDN, you have to understand the logical planes of network functions. So this network-wide policy compliance can be assured, for example, making sure all devices have the proper standard configurations, all devices have the correct software versions. This can be ensured if networks can be automated. Next, we'll see what a network device like a switch or router do. First, a switch forwards messages between networks by examining the information in the layer 3 header. Similarly, a switch forwards messages within a local area network by examining information in the layer 2 header. A router also uses a routing protocol like OSPF to share routing information with its neighbors and help them build a routing table. Similarly, a switch uses a spanning tree protocol to ensure that there are no layer 2 loops in the network. A router uses ARP, address resolution protocol, to build the ARP table. So ARP table can be used to map IP addresses to MAC addresses. It builds a MAC address table by examining the source MAC addresses of the incoming frames. So whichever interface the frame comes in, so accordingly the MAC address table will be populated. So both the router and switch may use a syslog to keep logs of events that occur in the network. So these are all the various functionalities of network devices like a switch or a router. So they may also allow a user to connect using a SSH and manage it. So you can connect to the CLI of a device through SSH and uh, configure the device. So all these functions, various functions of network devices can be logically divided into what we call as planes. Uh, Typically, we divide the device's functionality into three planes: the data plane, control plane, and the management plane. Let us take a look at the functions of each plane. First, let us look at data plane. So all tasks involved in forwarding user data are part of data plane. So this is what we usually think of a router or a switch doing, uh, like forwarding, for example. Sorry, yeah. A router receives a message, looks at the most specific matching route in its routing table, and forwards it out of the appropriate interface to the next hop or to the destination itself if it is directly connected to. It also de-encapsulates the layer 2 header and re-encapsulates with a new header destined for the next hop's MAC address. So all of these functions are part of data plane. So likewise, a switch receives a message, looks at the destination's MAC address and forwards it out of the appropriate interface, or it may flood it out of all the interfaces when none of the entries in its MAC table matches the incoming frame header. So this also includes functions like adding or removing VLAN types. So also functions like network address translation, which changes the source and or destination MAC addresses before forwarding, is also part of the data plane. So also deciding to forward or discard a message due to access control lists, port security, etc. is also part of data plane. Here is an example with two routers, R1 and R2. R1 receives a packet and the data plane processes the packet and it forwards it out of an interface to reach uh, router 2 R2. Router 2's data plane processes the packet to forward it out of another interface. So in this instance, R2 discarded a packet from R1. Perhaps an ACL configured on router 2's interface caused it to make that decision. Anyway, that's an action of the data plane. Now let us look at the control plane. So devices use their routing table, MAC address table, address resolution protocol table, and spanning tree protocol to make forwarding decisions. So functions that build these tables are part of control plane. So the control plane controls what the data plane does. For example, by building the router's routing table. So this task of control plane is considered to be an overhead work because it directly does not involve in forwarding frames or packets. So the control plane controls what the data plane does. Let me explain the statement with some examples. The OSPF protocol used by a router itself doesn't forward the user data packets, but it informs the data plane about how the packet should be forwarded to reach its destination. Likewise, a spanning tree protocol itself isn't directly involved in the process of forwarding frames, but it informs the data plane about which interfaces should be used and which should not be used for forwarding. One more example is the ARP messages aren't user data, but they are used to build the ARP table of uh, network device. So all these are part of control plane. So let us see what is the functionality of a control plane with an example. Both routers R1 and R2 communicate using OSPF protocol, and this allows both of them to build a routing table. So these routing tables control the actions of a data plane. So it decides where the actual forwarding of data packets takes place. So in traditional networking, the data plane and control plane are both distributed. So in fact, each device will have its own control plane, and the feature support of this control plane is depends on the vendor. Each device has its own data plane and its own control plane. So they are distributed throughout the network. So it is not one centralized control plane that controls the entire network. This is the scenario in a traditional network, whereas this is not the same in software defined network. So primarily we don't have a distributed control plane, we have a centralized control plane. So finally, let's look at the management plane. Like the control plane, management plane also performs overhead work. So however, management plane does not directly affect the forwarding of messages. Instead, it consists of protocols that are used to manage the network devices. For example, SSH or Telnet, which are used to connect to the CLI of a device to configure or manage it. Similarly, syslog, which is used to keep logs of events that occur in the network or a device. SNMP, which is mainly used to monitor the operations and status of the device. Also, NTP, network time protocol, is another example which is used to maintain accurate time across devices in the network. So you can configure the device time zone using NTP. So the control plane and management plane are both necessary to enable the data plane to forward incoming messages. So both of them help the data plane in making forwarding decisions. Here is an example of management plane. The network engineer uses secure shell, for example, to connect to the routers and do some configurational changes. For example, perhaps he configured OSPF, and now the control planes of the routers are using OSPF to exchange the routing information. This then determines how packets are forwarded in the data plane, and that's a basic summary of how these three planes work. The data plane is really the essential one for forwarding frames or packets. But in order for the data plane to do its job, we need the control plane and the management plane. So management plane is effectively what the network professionals directly interact with. So the operations of management plane and control plane are usually managed by the CPU of a device. So when I say CPU, it is a general purpose CPU. However, this is not desirable for data plane operations because CPU processing is relatively slow. So instead of the general purpose CPU, a specialized uh, hardware chip, application specific integrated circuits are used. So these are chips built for a specific purpose, such as forwarding frames in a switch. A switch, for example, when a frame is received, the the chip actually is responsible for the switching logic. The MAC table is stored in a kind of memory called TCAM. TCAM is content addressable memory. TCAMs are expensive as well as very costly. They are also very power hungry. So essentially, the ASIC feeds the destination MAC address of the frame into the TCAM. So the switch looks up its MAC address table to find a matching MAC entry. The frame is then forwarded out of appropriate interface to the next hop router or a switch. So now let us look at software-defined networking. SDN is an approach to networking that centralizes the control plane into an application called a controller. So SDN is also called as software-defined architecture or uh, a controller-based networking. So as I said earlier, the traditional control planes use a distributed architecture. For example, each router runs OSPF, shares routing information with its neighbors, and help them build their routing tables. So an SDN controller centralizes the control plane functions like calculating routes. Note that this I mentioned just as an example, and how much of control plane is centralized may greatly vary. So some functionality may be offloaded to the network devices themselves, and only a specific functionality can be centralized in an application called a controller. So SDN is not just about networking; it has the potential to play a key role in diverse applications. So the underlying technique used in SDN can be used in various use cases. For example, a German musical software and hardware company is leveraging the SDN concept to develop uh, modern music production kits by decoupling the musical notes and key functions from the underlying hardware and introduce a programmable software platform. So this platform allows the users to control the functions of different elements of the musical kit. So the idea behind software-defined networking can be applicable in various use cases. Now, depending on the SDN solution, the entire control plane might be centralized in the SDN controller, or perhaps only part of the control plane can be centralized. So this can leave some functions on the individual network devices. So there are many different SDN solutions available, and the role of controller and the network devices can greatly vary in each solution. So a controller can interact programmatically with the network devices using APIs, application programming interfaces. So this is our traditional architecture. Note that the purpose of this discussion, I'm leaving the management plane out. We are just focusing on the functions of control plane. Control plane to control plane interaction is done via OSPF in this example. Now I have removed the control planes from R1 and R2. Then we have a controller, an application running on a centralized server, and the control plane of network is centralized in the control plane. So instead of R1 and R2 using OSPF to exchange routing information and then building the routing tables, the controller communicates with R1 and R2 to program their data planes. So instead of control plane being distributed, each router having its own control plane, it is centralized in the centralized application called an SDN controller. So I'm only showing two routers here, but this could be a network with hundreds of routers, and this controller would operate the control plane of the entire network. So essentially, when the network size grows, the controller with limited capability may not be able to address the queries of all the devices. In that case, you can assume a logically centralized control plane where several instances of the SDN controller will control a group of devices, their own group of devices. So essentially, a logically centralized control plane can be uh, uh, used in such uh, deployments. So the communication between the devices and the controller is done via what's called a southbound interface. So OpenFlow is a de facto standard protocol that is used to communicate between the control plane and the data plane devices. It is called southbound because in a diagram we usually draw the controller on top and the network devices on the bottom, which is the south. So note that this southbound interface is not any physical interface on a device, but it is rather a software interface that is used to allow the controller and the network devices to communicate. So now, before moving on to the next slide, I wish to reiterate the fact that although this diagram shows a totally centralized control plane, there can be a different solution. Some of them centralize the entire control plane, and some of them only centralized some functions of the control plane to enable scalability. So in this slide, we'll try to understand more about APIs. APIs are used to allow programs to exchange information between with each other. So they are important for network automation because they allow our programs to easily interact with network devices and the controller. So in SDN architecture, APIs are used to communicate between apps and the SDN controller via the northbound interface, and between the SDN controller and the network devices via the southbound interface. So netconf and restconf are popular southbound interfaces. The northbound interface typically uses a REST API. REST can be expanded as a representational state transfer, representational state transfer API. So let us look at southbound interfaces. The southbound interface is used for communication between the controller and the network devices it controls. So in the diagram, uh, which you have seen earlier, yeah. So this R1 and R2 are controlled by the controller, and the southbound interface is used to communicate between them. So the SBI typically consists of a communication protocol and the API. So basically, they are they are used to facilitate data exchanges between programs in a standard format. So the controller is a program, and the network devices are also programs running within their hardware. So the data is exchanged between the controller and the network devices. And for example, an API on the network device can allow the controller to access information on them, as well as control their data plane tables, and also may use them to forward packets or frames, etc. So APIs play a big role in automating network tasks. So we'll go more in depth later. So here are some examples of southbound interfaces: OpenFlow, Cisco Opflex, Cisco 1PK, and Netcon. Remember, they are southbound interfaces used by the controller to communicate with the devices it controls. OpenFlow is the predominantly used southbound interface. So in addition to southbound interface, there is also a northbound interface. So to review using the southbound interface, the controller communicates with the managed devices and gathers information about them. For example, which devices are in the network, the topology, network topology, how the devices are connected together. All this information is gathered by the controller and maintained at the centralized server. So that's about southbound interfaces. So the northbound interface NBI is what allows us to interact with the managed devices and gathers information about them. So it gathers information like the pro, I mean network stats, for example, etc. So it can also make changes in the network via the southbound interface. So essentially, an application will interact with the controller. The controller will interact with the forwarding devices. So this is the basic architecture of a software-defined network. We can tell the controller to make a change, and using the application, it will make the change via the southbound interface. So here we have an application, and it will use the northbound interface to communicate with the SDN controller. The SDN controller will interact with the forwarding devices using the southbound interface. So I explained that name northbound interface already, so I think you can guess why this is called the uh, northbound interface. So I explained the so northbound interfaces are commonly used for making configurational changes or automating network tasks in the network. So unlike the prerequisite for network automation in traditional networks, devices need not all follow the same configurations. Some devices may have a few devices can have a different network policy, and few other devices can have some other policy, but both can be controlled with the same SDN controller. So a REST API is used on the controller as an interface for the applications to interact with it. REST stands for representational state transfer, as I explained. Just note that REST is not a specific API, but it is a type of API. It is like a standard. It defines how a REST API should uh, act. So there is an interface on the controller as I mentioned earlier, this is not a physical interface. It is the API that facilitates communication between the controller and the application. So predominantly, REST APIs are used as northbound interfaces. So the applications are on the top, the controller is in the middle, and the network devices are at the bottom. So actually, these three layers of the architecture have names. On top, there is the application layer. This layer contains scripts and applications that tell the SDN controller what network behaviors are deserved or desired. Next is the control layer. This contains the SDN controller that receives the process information from the application layer. And finally, there is an infrastructure layer or the data plane, which contains the actual devices that are responsible for forwarding messages across the network. So I did not mention these layers before. So the application layer contains apps and scripts for instructing the SDN controller. The control layer contains the SDN uh, controller, and the infrastructure layer contains the network devices. So for example, an application sends a get message to the API, for example, which is a request for some data. The controller will respond with the requested data in a structured format like JSON or XML. So next, let us look at the term fabric. So to understand fabric, we need to understand two other terms, the overlay and underlay. First, the underlay is underlying physical network of devices and connections, wired or wireless. So this provide IP connectivity, for example, with a routing protocol like ISIS, which is intermediate system to intermediate system. So layer 3 switches usually use ISIS as protocol for uh, building their routing tables. Usually, actually, routers mostly use OSPF as their protocol for building the routing table, but layer 3 switches uses ISIS as their uh, routing protocol. So basically, the underlay is a bunch of multi-layer switches and their connections. So the underlay purpose is to support the VXLAN tunnels of the overlay. So basically, overlay is a uh, virtual network that is configured over the underlying physical network. So to make a virtual network of tunnels, the devices first need to be connected and they should be able to reach each other, for which the underlay uh, support is needed. So there are three different roles of switches. Those are edge switches. So these are switches, edge switches are switches um, that connect to the end hosts like a traditional access layer switch. Then there are border nodes which connect to devices outside of the domain, for example, connecting to a WAN router. And finally, there are control nodes which use a protocol like a list locator ID separation protocol to perform various control plane functions. So the overlay is the virtual network built on top of the physical underlay network. So for example, virtual extensible LAN can be used to build tunnels, VXLANs. So and fabric is the term we use to refer to the combination of the overlay and underlay. The physical and the virtual network as a whole we call as a fabric. The overlay network consists of VXLANs tunnels. For example, between these two switches, when hosts in the LAN communicate with each other, their traffic is sent over a VXLAN tunnel. This is the overlay network. And fabric refers to the physical and virtual network as a whole, overlay plus the underlay. So before we see more about data serialization, uh, let us quickly compare the traditional networks with SDNs. So we have been looking at SDN a lot, but networking tasks can be automated in traditional network architectures also. For example, scripts written in Python can push commands to many devices at a time. But as I mentioned earlier, for that to happen, all the devices should support the same configuration. They have to have a specific template. Otherwise, what happens is for the same instruction, each device will respond in a different manner. So the script can enable your computer to SSH to the device and then push whatever commands you want. Uh, Perhaps you can configure the VLAN on a switch. Also, Python with good use of regular expressions may also help you to parse through the show commands to gather information about network devices. For example, show interfaces command will give you a text of data. Using that text data, you will parse through the data to find out useful information like the bandwidth, etc. So the centralized data collected by the SDN controllers greatly facilitate these functions. The controller collects robust information about all devices in the network, providing a centralized view. So also the northbound APIs allow apps to access information in a format that is easy for programs to understand. So these formats such as JSON or XML, YAML uh, are the standard data serialization formats. So these formats help you to avoid writing scripts to pass through the specific show commands. So also having the centralized data facilitates network-wide analytics rather than getting information from individual devices and having to correlate the data yourself. So since you have centralized information, you need not do any further processing. So SDN tools provide the benefits of automation without the requirement of third-party apps and scripts. So this also means that you don't need expertise in automation to make use of SDN tools. So many of them are very easy to use even for those who are unable to write their own scripts. So most of them use a generic programming languages. So to summarize, although SDN and automation are not the same thing, SDN is just one aspect of network automation. The SDN architecture greatly facilitates the automation of various tasks in the network using the SDN controller and the APIs. So next we'll try to understand why data should be structured. So the structured or formatted data makes it much easier for programs to use it because it is stored in a standard format that is easy to interact. So in this module, we'll look at JSON, XML, and YAML. So these are known as the data serialization languages or data serialization formats. So these allow us to format or structure data in a standardized way so it can be communicated between applications. So let us take a look at what data serialization is. So it is the process of converting data into a standard format or structure that can be stored, for example, in a file or transmitted, for example, over a network, and then can be reconstructed later perhaps by a different application. So why is it useful? It allows the data to be communicated between applications in a way both applications can understand. So if one application is written in Python and some other application is written in Java, both languages store data differently. So they need some standard format to send data between each other. So data serialization languages, for example, JSON, allows us to represent variables with textual data. So here are some examples of variables. For example, interface name, gigabyte Ethernet 11, status of IP address 192.168.1.1, and netmask 255.255.255.0. So these are four variables. Basically, variables are containers that store these values. For example, interface name is a container and it contains the value gigabit Ethernet 11. Status is another container, and so on. So let us see how data exchanges would work without the use of a standard data serialization format. So in that case, data will be sent in a format which is not understandable by another application. So the application cannot parse the data to understand what the data was sent. So the app and the controller are programs written in different languages, and they store data differently. They cannot communicate directly. Uh, because the variables are in a standard format, both the sender and receiver can understand it. So the client is able to take those variables and convert them into its own native format. So this is how data serialization formats like JSON or XML are used for. So now let us take a look at XML. XML was developed as a markup language, but it is now used as a general data serialization language. So you know what a data serialization language is, but uh, what is a we'll see. For example, HTML you might have probably heard of is a markup language. So XML is generally less human readable than JSON, although it is not so difficult to read. Uh, in JSON, white spaces are insignificant. Say in the same way, in XML, white space is also insignificant. So although you'll often see it displayed with spaces and line breaks to make it more human readable. XML is also often uh, used by REST APIs, same as JSON. So the general format you need to know is the key is tagged like this. So with the value in the middle, XML is generally thought to be less human readable than JSON. So that's all for XML. So finally, let us take a brief look at YAML. The name YAML originally meant yet another markup language. So, but to distinguish its purpose as a data serialization language rather than a markup language, it was rephrased to be YAML. YAML is used by the network automation tool like Ansible. We'll see Ansible shortly. YAML is very human readable and white spaces are significant. So indentation is very important. We are not free to format the text however we want. YAML files start with 3 hyphens and single hyphen is used to indicate a list. So key value pairs are represented as key value. So here is an example of YAML script. So this is the same interface which I was showing in the previous two formats, JSON, XML, and YAML. Next, we'll see REST APIs. Before we understand REST APIs, let us try to understand operations of REST APIs. So let us take a look at create, read, update, and delete operations. It refers to the operations we perform using REST APIs, but the framework isn't just used by the REST APIs. So first, let us look at the definition of each of these operations. So create operations are used to create new variables and set their initial values. For example, you could create a variable IP address and set the value to some 192.168.1.1. Read operations are used to retrieve the value of a variable. For example, you could then ask what is the value of a variable IP address. Then it will respond with the IP address of that device. So update operations are used to change the value of a variable. You can change the value of a variable IP address to some other IP address. And finally, delete operations are used to delete variables. So you could delete the variable IP address. Now let us look at HTTP first. Why should HTTP uses these CRUD operations create, repeat, create, read, update, and delete. And these CRUD operations match the actions we typically want to perform with an application. So when a HTTP some client sends a request to a HTTP server, it includes a where indicating what the client wants to do. So the uh, methods HTTP requests can be sent are post, get, put, or patch, delete. So and for this reason, among others, REST APIs typically use HTTP as their application layer protocol to communicate with the uh, over the network. So as I was talking about REST APIs, REST is not a API, but it describes a set of rules about how APIs should work. So REST APIs are APIs that follow the REST architecture. So the next characteristic I want to cover is the REST API exchanges are not stateful, they are stateless. So statelessness means that each API exchange is a separate event independent of all past exchanges between the server and the client. So for example, your computer might cache many elements of a web page so that it doesn't have to retrieve the entire page every time you visit that web page. So this improves the performance of a client and reduces the load on the server. So in this module, in the second module, we'll cover configuration management tools, Ansible, Puppet, and Chef. So first I'll introduce configuration management tools, what they are and why we use them. Then I'll introduce some of the characteristics of the configuration management tools. Configuration management tools like Ansible, Puppet, and Chef can be useful in any network, but especially in medium to large scale networks with hundreds or even thousands of devices. These configuration management tools can be used. So to understand one reason why configuration management tools are useful, let me explain the concepts of configuration drift. Configuration drift is when individual changes made over time causes the devices to deviate from the standard and correct configurations as defined by the uh, organization. So this is not a good thing and should be avoided whenever possible. So although each device will have unique parts of its configurations, for example, IP address, host name, etc. Most of the devices configuration is usually defined in the standard template designed by the network engineers of that company. For example, you can expect all of your routers to have the same SNMP configurations, the same syslog configurations, or the same access control lists. So one or two local area interfaces or a loopback interface, etc. So these all follow the standard template. So with just a few unique configurations for each device. But as individual engineers make changes to the devices, for example, troubleshoot and fix network issues, the test configurations, etc., this configuration of a device can start to drift away from the standard template. So often records of these individual changes and their reasons are not saved. So the configuration management tools will look um, will help you with this. But even with automation tools like Ansible, it is best to have standard configuration management practices. So as we know, traditional configurations provisioning is done by connecting to the devices one by one via SSH or console port. So, but this is not practical in large scale network. So it simply do not scale well in networks with hundreds or thousands of devices. So configuration management tools like Ansible, Puppet, and Chef allow you to make changes to devices on a large scale with a tracking and effort. You can also access it remotely. So two essential components that you'll find in all these tools are templates and variables. So basically a template is a file that uses that values are not given to for example containers like hostname, IP address, mask, OSPF, process ID, etc. So instead of saving the values, we use a separate file specifying the variables for a specific device, for example, router R1. So when given a template and the appropriate variables, a configuration can be generated and that configuration file can be sent to that device. So these configuration management tools are network automation tools that facilitate the centralized control of large numbers of network devices. So they can be useful in networks for any size, but typically they are used in large scale networks. So the options we will be learning today are Ansible, Puppet, and Chef. So using templates, it is very simple to generate a new configuration for a new device. So it is just a uh, uh, it is just a copy paste of some few values. So they can be used to perform configurational changes over the devices. So these configuration files can be generated for all the devices in the network at a time, or you may also choose a subset of devices and generate configuration files for them. So not only just generating the configuration file, the devices uh, actually these can all be used in network or certain set. So if the device's configuration doesn't match the standard, so for example, an alert can be sent to the uh, network administrator to make necessary changes. You can also compare configurations between devices and between different versions of configurations on the same device. So these are just some examples of what you can do with these tools. So basically, they solve the problem of managing the configurations of devices in networks with hundreds or thousands of different devices. So let us quickly walk through few configurational uh, features of Ansible, Puppet, and Chef. So Ansible is a configuration management tool owned by Red Hat. So Ansible itself is written in Python. It is agentless. The other two I will introduce, Puppet and Chef, are written in different language, Ruby. So it means Ansible does not require any special software to run on managed devices. So it uses SSH to connect to devices, make configuration changes. It may also fetch some information from the devices. So this is a basic advantage of Ansible, which makes it very versatile, and it is probably the reason that it is the most popular choice of network device configurational uh, management tools. So Ansible uses a push model. So the Ansible server, also called as the control node, uses SSH to connect to the managed devices and push configurational changes to them. So the other two, Puppet and Chef, which uses a pull model in which the managed devices connect to the server to receive their configurations. So after installing Ansible, you must create several text files that it can use. Playbooks are the blueprint of automation tasks. So these are the files it needs to be generated. So next is the Puppet. Puppet is a configuration management tool written in the programming language Ruby. So it is uh, typically agent based. So which means the specific software, uh, a Puppet agent must be installed on the managed devices for configuring them using Puppet. So however, it can be run agentless, in which a proxy agent runs at as an external host, and the proxy agent uses SSH to connect to the managed devices and then communicate with them. So note that in Puppet, the server is called the Puppet master. Puppet uses a pull model. So clients pull configurations from the Puppet master. So instead of Puppet master pushing configurations to them, it uses a pull model. Note that the clients use TCP 8140 to communicate with the Puppet master. So and instead of YAML, it uses a proprietary language for its files. Like Ansible, it requires some different text files on the Puppet master. For example, a manifest file defines the desired configuration state of the network device. Puppet communicates using HTTP via the REST APIs. Finally, let us look at Chef. Like Puppet, it is a configuration management tool written in Ruby. It is agent based. So specific software like HF agent must be installed on the managed devices. And like Puppet, Chef also uses a pull model. Chef uses TCP port 10002 to send configurations to their clients. Also, Chef uses files like domain specific language, which is based on Ruby. So they define configuration objects managed by Chef. So as I mentioned earlier, these tools were not designed specifically for network devices. They can be used for various purposes. Puppet and Chef uh, can also be used for uh, tasks like where data exchanges are needed between applications. So Puppet and Chef communicate using HTTP via the REST APIs. So that is for Chef. So now in module 3, I'll introduce IIoT. IIoT is characterized by the massive integration of smart objects, machines, sensors, cyber physical systems of modern day industries. So they can be of different types: machine to machine, human to human, human to a thing to thing, and thing to things. So it brings immense value into our lives, touching areas such as health monitoring, green energy, and environment monitoring. IIoT enables to revolutionize the industrial sector through the power of connected machines, sensors, and devices. So the number of such integrated devices are estimated to run into billions in the next decade. However, IIoT focuses heavily on machine-to-machine communication and machine learning and big data. This enables uh, organizations to unlock access to unprecedented amounts of data and rapidly extract insights of continuous improvement of product services and processes. So a recent survey by Microsoft found that 91% of companies have at least one IIoT project in their uh, works. So a forecast by some other company called Million Insights predicted that the IIoT market could reach $992 billion in global spending in the year 2025. So this growth will enable cost effectiveness and the ease of availability of required devices like processors, sensors, and connected systems. So it brings immense values into our life. So in order to save the operational cost of implementing IIoT systems for industrial automations, the subsystems and individual processes that make up the industrial IoT system must have the available resources, and that resources should be fairly distributed according to the requirements of the processes or subsystems. So here is where SDN and NFC are two of the latest technology designed to introduce flexibility in network management and orchestration of network resources. So virtualization has made network provisioning and automation more feasible and dynamic than the traditional approaches. So due to the full software-based control of different network elements. So instead of having a hardware firewall or a load balancer in your network, you can deploy it as a software application, and that is enabled using the NFV. Resource orchestration is another focal point for effective IIoT implementation. So considering that IIoT networks consist of a large number of diverse applications with diverse resources and SLA requirements. So as such, there is a high tendency for multiple nodes to the same resources, such as the time slot to send data, transmission channel, power of other computational resources, etc. So the so with such unpredictability, resource orchestration can be quite complicated, even in basic use cases, and almost impossible to handle in some extensively dynamic use cases. So because of the heterogeneous nature of IIoT devices and services, so the need for analyzing and processing data generated by smart devices in real time leads to high delay, poor bandwidth utilization, etc. So to overcome all the issues mentioned earlier, a flexible and programmable network technology is necessary. Since SDN is a flow table driven communication paradigm, forwarding can be done faster by efficient management of flow table entities. So integration of smart grid with software defined networks not only provides faster and reliable communication, but it also leads to an efficient control. So the SDN IIoT model helps to handle various network issues such as flexibility, global traffic monitoring, programmable network policies, fault tolerance, and dynamic routing for large scale networks. So the integration of SDN and IIoT provides true realization of the dynamic nature uh, required for the industry uh, in the current trend. So despite the proven ability of SDN to offer dynamic traffic programmability and create a policy driven network supervision through the control functions, they suffer some challenges. One important but much less explored area is ensuring adequate security in SDNs. So security is one major concern in SDN enabled networks. Also due to the technological advancements, SDN devices had to work with the traditional devices in a network because all the networks are already equipped with traditional networks. So the reason for SDN enabled device to support the traditional functionality is due to the fact that it should interact with traditional networks which are already deployed. So that is the reason why they are priced high. But as SDN as a technology emerges into the enterprise networks, this expenditure is expected uh, to be much lower than the traditional network devices because the devices need not have the intelligence. It is just a forwarding. Uh, it should have a forwarding logic just to forward incoming packets or frames. So, however, the controller as an application can be uh, more standardized in the coming years. So, one more challenge is the device interoperability. As we have discussed, the SDN controller has to uh, work with both the traditional devices as well as the SDN enabled devices. So uh, attaining interoperability among them is also a challenge. So the amalgamation of IIoT and SDN enables, elevates the security concerns because of the increased programmability of networks. Networks become much more open to vulnerabilities. So these are some of the references. I'll share this PPT with you. So that's all for now. Now, if you have any questions, you can ask me. You can kindly unmute and ask me. I'll be glad to respond to queries.
A few minutes, participants. Dear participants, any queries, you can unmute and discuss with sir. Or you can post that in chat box. Any queries? Any queries, participants? You can unmute and you can ask your questions. Or in chat box.
Give them access to chat so that they can.
No, it is accessible.
But it is showing no longer has access to chat.
Thank you very much.
Okay, correct. Okay. Shall we wind up, madam?
Can we conclude the session then?